Okay, let's look at the same square root of 25 that I had in my previous video, except now I'm going to throw in a variable. I'm going to throw in an x squared. Now this is a perfect square because the square root of the 25 is just a 5. Square root symbol's gone. But now we're going to look at the x squared. The square root of x squared is just an x because x times x is x squared. Just like 5 times 5 is 25, or I guess you could say 5 squared. Ooh, look at that. If you take the square root of anything that is squared, you just get the anything. The square root of a 5 squared would just be the 5 because the square root of 25 is 5. Anything squared. This square root sign and this squared would just cancel each other out. Or you could think of it like this. You could think, I know this is a square root. There's really an invisible 2 right there. If you have a cubed root, they put a 3 right there. If you have a fourth root, they put a 4 right there. But since square root is the smallest, they never put the 2 right there. But really, it's there. It's just invisible. It's hiding, okay? And you could say, okay, 2 divides into 2 one time. So what I really have here is a 5 to the first. But that first is also invisible because 5 to the first power is just 5. So that's kind of a shortcut, the division, because if I have something higher, like let's say the square root of x to the 6th, 6 divided by 2 is 3. This is going to be x cubed. But that's because x to the 6th is an x cubed times an x cubed. Or the square root of an x cubed that got squared. And then this squared and this square root cancel each other out. And all you're left with is the x cubed. X cubed. But I like to do the division. I'm like, here's the 2. 2 divides into 6 3 times. Or you can say 6 divided by 2 is 3. This ends up being your new exponent. This trick only works on exponents. It doesn't work on these guys unless I suppose you rewrote it like this, which most people don't do that. They just remember the list of perfect squares that I had written out in my first video. So, and this trick will work on cubes also. If I had the cubed root of, let's say, x to the 12th, that's going to end up being x to the 4th. 12 divided by 3 is 4. Because you're really looking at x to the 4th times another cube root of x to the 4th times a cube root of x to the 4th times another cubed root of x to the 4th. So what I've really done is the cubed root of an x to the 4th 3 times. I did it 3 times. 1, 2, 3. That's this 3. X to the 4th cubed. Because 4 times 3 is this 12, if you went backwards. And your this 3 and this 3 cancel each other out, and you're just left with the x to the 4th. So the variables, that works. Now this example is just of perfect squares or perfect cubes. If there's anything left over, that's a different situation. So let's look at that one too. I already saw this up here because I know in my last video we started with the square root of 25, but I then took you to the square root of 32, and you had to literally break that down to be the square root of 16 times the square root of 2. The square root of 16 is 4, but the square root of 2 just stayed. That's simplifying the radical. The same thing works with variables. Let's say I had the square root of x to the 7th. Now, if you remember even numbers, remember there's really a 2 right here. Any even number is divisible by 2. 2 goes into 2, 2 goes into 4, 2 goes into 6, 2 goes into 8. They all go into it evenly. It does not go into odd numbers evenly. There's always 1 left over. If you take 2 and divide it into 7, 2 goes into 7 3 times, because 3 times 2 is 6, and when you subtract, there's 1 left over. There's a remainder of 1. So if you break this down, you have to break it down to be the square root of x to the 6th times the square root of x to the 1 left over. And then the square root, this is a perfect square. 2 goes into 6 3 times, so this becomes an x cubed. The square root of x to the 1st is still just the square root of x to the 1st. I would just not write the 1st because it's really invisible. And that would be breaking down the variable part. So the square root of an x to the 7th becomes an x cubed times the square root of an x. Let's say I was taking the square root of, I don't know, let's switch to different letters. How about n to the 11th? If you want to use the trick, that's a square root, I would say 11 divided by 2. 2 goes into 11 5 times. That's 10, right? With 1 left over. So my exponent is now n to the 5th. This is going to become an n to the 5th times the square root of an n. Just like over here when I divided, 2 into 7 went 3 times. Here's my x to the 3. And then my x to the 1 left over, here's your x, well, there it was, x to the 1 left over. So on this 1 right here is really an invisible 1 right there. But if you break it down, if you'd rather break it down, you can say that this breaks down to be the square root of n to the 10th times the square root of n to the 1. 10 and 1 adds up to 11. And then the square root of n to the 10th is an n to the 5th, and this is just the square root of n. And that's your answer. I hope that makes sense. If it's a cubed root, because I think I did cube roots, I don't know. Let's say if it was the cubed root of x to the, okay, I need a number that 3 does not divide into evenly. How about 14? Okay, so 3 divides into 14 4 times, because 3 times 4 is 12 with 2 left over. So this is going to become I'm going to write it down lower, an x to the 4th times the cubed root of an x squared. This 4 right here is this one, and this 2 right here is that one. Because if you want to take a cubed root of an exponent, the number has to be divisible by 3. So if you wanted to break it down instead, like this, erase this, I would have to break this down to be 2 different cubed roots, both with x's, but the first one would have to have an exponent that 3 goes into, which would be 12. And then I'd have 2 of them left over, because 12 and 2 adds up to the 14. And then the cubed root of x to the 12th, this one here, becomes x to the 4th, and then you still have the cube root of an x squared. I hope that makes sense.